associate professor in the Department of Electrical Engineering and School of Artificial Intelligence at IIT Delhi. He heads the Machine Intelligence Signals and Networks Lab at IIT Delhi. His current research focuses on graphical models, manifolds, semi-supervised learning, and large-scale optimization. He received his MTech and PhD degrees from IIT Kanpur and completed his postdoc from the Hong Kong University of Science and Technology. The overarching theme of his research efforts lies in the coherent interaction between optimization, machine learning, signal processing, and graphical models. Once again, welcome Sandeep Kumarji. Now you can share your screen and start your session.
Thank you.
Thank
Thank you. So thank you, Dr. Ravi, for the invitation. Is my screen visible to all of you?
Yes, it's visible.
Okay. So am I audible?
Yes, you're audible.
Okay. Thank you. So the theme of my talk would be on the graph machine learning. I primarily work in the area of graph ML, and I will not be talking much directly related to 5G and 6G and wireless communication, but I will be talking about the tools and methods which are still very relevant for these technologies. Just to give you a very brief intro about me, I did my master's and PhD from electrical engineering department, and there my core area was wireless communication and signal processing. Of lately here, I have migrated from communication and signal processing research area to ML, and from the ML, I still do the same thing what I used to do, mostly focusing on algorithms. But here I just focus on generic algorithms which can be applied to any domain. But the kind of a training what I received during for the communication and signal processing background, I still find it very important, and those gave me the foundational basis to explore the machine learning areas, mostly related to algorithms relating to convergence and so. Okay, so let's start with graph machine learning. Okay, the idea is very simple here, that we need to, there is a kind of a data set, data structure, which have both nodes and features, and the nodes are connected, and connections have certain meanings if they are, and if you, and also in between, if you have any queries, feel free to let me know. Like, I will be happy to answer any of your queries in between. Okay. Yeah, so the kind of a data structure that we have in here is that there are entities. Entities could be anything like two persons, two base stations, right? Or one base station, one user, anything, right? And if they are related in some manner, then there will be an edge, and the edge will have certain values. So the values will simply encode how strongly they are related and how strongly they are not related. When we say graph data or also graph signal, so on top of that data, on top of a graph or for each node, if we can have any features associated with it, then we call those as a graph data, graph signal. Examples of graph data are ubiquitous. I think it's omnipresent, from traffic graph to social graph to brain network to economic activity network to molecules to precipitation graph to circuit graph to ever to also the image graph. So every simple thing, everything around us can be, or if you there is a, if you want to utilize the inherent structure into it, then you can definitely represent graph, the data set, as a graph data, especially in wireless communication for resource allocation, right? For interference alignment, for you can say reflected surface kind of a thing. There's all, for all these things, graph is very natural, right? And there are different structures of graph, like bipartite graph and so on. So graph is still very important and relevant in wireless communication technologies. So again, why I am talking about graph? So very recently, I just went through the nature's uh, nature portfolio to see how well the graph-based framework is shaping the overall area. And these are some of the very recent work on nature, like nature communication, like machine intelligence, to just see. So you can see the graph-based ML framework, a graph-based framework are overlapping with almost all the domains, from the free trimetallic electrocatalysis study to quantifying spatial heterogeneity of urban networks to the learning neural networks for ligand, like the ligand affinity. So you can see that almost all the domains graph-based framework are helping. And there was also a review in Nature that talked about how graph-based ML or graph-based representation is going to change the next frontier of research. And before the LLM, you can say popularity, graph-based ML was one of the top or hot topic for theoretical and applied ML researchers, right? But why so? Why the graph-based things we are so much talking about, right? So most of the analysis that we have done so far are restricted to the understanding of that the data set sits on the Euclidean space, flat world. And those are still good. And all the analysis like the Euclidean distance, you can say, or the Hilbert space kind of assumptions are very much valid there. But if we really want to move beyond and try to handle the specific types of data sets, right? For example, your gene regulatory data, for example, the customer like satisfaction for quality of service data, these kind of data sets, they are typically very irregular and they are on a very irregular spaces and surfaces, right? So data has shapes. So existing framework without this graph methodology are not able to capture the shapes of the data. So in order to build a meaningful model or meaningful algorithm, right, you need to have a very good understanding of the data set, that the understanding of the data regime that you are working on, right? So you need to represent that data. So representing the data, just to give some context. So if you have very irregular surface and the flat world assumption will not hold, so what will work there? In that case, it has been established that if you can represent each data point as a kind of a point cloud point and then learn the graph structure over it, and if a graph is meaningful, then you are able to represent that the complexities of the data. So fast forward, it is saying that the graph-based representation of the data can give you a very good approximation of the irregularities or the complex structure present in the data. Just to relate it with a very practical equations, many of you might have studied these equations like Laplace equation, heat equation, wave equations, curvature, isometry invariance, frequency decompositions, all involve this delta U term. And delta U term, you'll not get into the details of it, just for the connection, you will be able to, if you want to understand more about it. It just gives a connection that the many of the physical phenomena also, there we need to understand that you need to understand the neighborhood structure of it, right? In the Laplace equation also you need to understand how are my values at this location, if you're looking at the Laplace or heat equation, is different from the neighborhood, right? We want to also understand the curvature. There also the neighborhood criteria becomes important. And similarly, some of partial derivatives, differential equations to each and everything. There, all these physical phenomena have a very close approximation with the Laplace operator. And Laplace operator in the continuous domain, when you want to approximate the continuous domain in the discrete domain, the graph-based Laplace is the closest approximation, where that is utilized to capture the graph-based representation of the data. Just to give you a big connection, whether you are working in whatever domain, but this is one of the frontier which is going to be which is very powerful. It gives you a lot of flexibility in types of the representation of the data. And as I have given some examples before, that almost all the domains, if there is a relationship in structure that you want to capture, neighborhood structure that you want to capture, then you can utilize the graph-based data. So a very rough, big picture idea of why this is making sense. Why they're making sense is that suppose your data sets are lying on this curvature, that could be anything. So how graph-based representation helps? So when you're having the data set on the curvature, the usual sense of distance metric do not make sense. For example, the point here, if I am this, I am not, let me use something. So if I am here currently, and if I am here, next point is this. If I will just use a regular distance between these 2 points, right? Then the distance between these 2 points would be smaller. But which we want to capture the structure of it, the distance from here to here will have to follow this curvature, right? So the regular distance or the regular geometry that we have been exposed so far are not able to, will not be able to sufficiently capture the curvature or the complexities of the data. But suppose if you have learned the graph structure well, then the graph-based distance would be a true representation of the actual distance between the data, and then you can compute whatever you want to do. So the overall pipeline is something like this. If from many of the data sets, if graph is given to you, then no worries, you can directly utilize in the pipeline. But if a graph is not given to you, then what you do? From these data points, you learn a graph structure. Suppose if you learn the graph structure, then use that graph to build the further models. Okay. And when we have the graphs, right, then there are three popular frameworks. Before the deep learning, there were was the label propagation based method, and other was the smoothness and the regularization based method. With the deep learning, there is something called graph neural network. In graph neural network, again, you pose problem as a graph data. And on top of that, either you learn the node level prediction, you talk about the individual node, or you talk about the edge level prediction, where you need to do study something about whether there should be a link between these two nodes or not. And there is a graph level problem there, whether you want to build some ML model over the entire graph. While the two classical frameworks, in the classical frameworks, you can think that for this kind of a graph, it is a handwritten digits. If I know the labels of this node and this node, then label of this node would be nothing but the summation of the neighborhoods, right? So this is based on the labelhood propagation. So was I audible throughout or not audible?
Yes, sir, you are audible.
Okay, there was some noise in between. Okay. Okay, fine. Okay. So there are two types of methods earlier. One was the label propagation based method. So there we propagate the labelhood information among the label based information among the neighborhood, and other was a regularization based method. So if you have done optimization kind of a routine for your wireless problems, so you must be exposed to the idea of regularization. So there with your objective function, whatever you were solving, you also add a regularizer which are graph based, right? So these are overall popular big picture of a graph-based ML. I will now try to get you to certain details of the flow, and let me give you a broader context at how we approach any graph-based ML problem. So far, if you have any question, please let me know. I will just give you more context to the problems in some greater detail. Okay, so if you do not have any further question, let me just start it, right? So this is the overall general idea of graph ML, graph-based signal, graph signal. Each node could be anything, and with each node there are certain features, right? And now we have to understand how are these features related to each other, right? Just to give you some context, if want to do the traffic prediction or you want to estimate the expected time of arrival, then the road network is your data. In that case, nodes are no road junctions. Nodes are road junctions, edges are road connections, and signals, the features are nothing but the traffic congestion at each junctions. If you want to deal with the semi kind of the identifying, suffer some of the nodes, or maybe the friendship or the social network data. Individual nodes are each person's. Friendships between them are the connections between these two nodes, and signals are the preferences and behavioral dynamics. Okay. So this is also an example of graph data. Similarly, there is a brain network data. So in terms of this, if you there are different regions in brain, and we capture the regions, some signals from each of the region, and the signals for each of the region are correlated with the signals of other region. So they also give a sense of a graph. So in this case, what would be a graph? Graph would be nothing but each of the brain region. And what are the edges? Edges would be the interconnection pattern, that how they are functional connectivity, and features would be the blood oxygen level dependent signals. Similarly, for economic activity network, there would be each country would be a particular node. Their financial transactions or economic connections would be the edges, and the signals would be the volume of trades and commodity exchanges. Images are also a popular type of a graph data. So when we have a graph based data, either you can solve as a, whether given an image or graph, what kind of a, whether it is suffering from any like whether you want to do some kind of a classification, or you want to do some kind of a regression thing. I just want to understand, any one of you have you a bit of understanding of machine learning, or you are completely unaware of the machine learning examples? Can someone please give me some sense? Otherwise, I will have to skip these words, or maybe need to explain in a different manner. Hello?
So
So
they can only
our
they can
attendees,
only give the chat.
so
They
attendees
can answer
cannot
the
ask
chat.
questions, right? Hello? So attendees cannot ask questions. So if there will no response, I will have to conclude this session. There is no point me talking, right? Hello?
Yeah. Good evening, Sandeep Kumar ji.
Yeah, yeah.
Yeah,
ये
just a second.
नेटवर्क चला गया था या है?
नहीं, we are all here.
Okay. Yeah, I just want to
And
understand very, very high level. Okay, do they have any ML background? Because I have been using ML words. So can I continue with those words, or should I need to avoid it? Just to have a rough sense of the composition of the
Yeah.
participant.
Participants, please. Actually, participants do not have the option to unmute. So, what we normally ask them is put whatever they can on the chat.
Okay, fine. So I will assume that they have some bit of understanding, and then I will move to the discussion. If they
Yes.
have any queries, please feel free to
Yeah,
give.
they'll post on chat, and well, there is one participant who's telling that you can skip the ML part.
Okay.
Okay.
Okay, fine. So let's just try to understand. The theme is to have graph ML. So I will skip more discussion on ML just to give you that how you can start using it in your framework. So in many of the cases, what it is there that you have nodes, right? And I am just taking example of nodes as a person. It is easy to connect with, and you do not have the connection understanding between them. And these examples could arise in many ways. Many ways like suppose you if you want to suppose you want to build a kind of a collaboration network, right? Collaboration network between different enterprises, or you want to build uh, some kind of a connectivity network. So initially, for those nodes, you do not know whether how are these nodes connected or not. But just based on those features, you need to establish whether the connections exist or not. Okay. So this is a very fundamental problem of graph learning from data, and these kind of problems would occur very frequently in many of the domains. So you want to utilize graph-based representation, but graph is not known to you, only individual nodes are given to you. So this is a problem of graph-based learning. But how do we how do we learn? So how do we start from features to learning of the graph from the data? Because once you have the graph representation, then it is very straightforward to apply existing techniques of either graph signal processing and graph neural network, because you can directly call the functions. If you don't want to get into the details of ML, you can directly call the functions and build. But in your domain, if graph is not given to you initially, then how you will deal with it. So let me just give you a few context. There are primarily, you need to start with the models, right? What are the different types of models of a graph representation? So primarily there are two types of graphical models. One is a sample correlation based, and another is a similarity function based. Sample correlation means you have two pairwise nodes, okay? And just for one feature, you just look at two features directly, and whether those two features are correlated or not, based on that you decide whether they are connected or not. So these are known as a pairwise dependency, because if I'm establishing a connection between two nodes, I'm not looking at other nodes, I'm only looking at the pairwise nodes. These are good, these are very helpful, very easy to deal with. But these models primarily underlook the overall global structure. Okay? And in some cases they are not optimal. So would be the second way? Second way is that there is some kind of a hidden structure present from the data, and you need to not only look at two nodes, just pairwise nodes, you also need to look while deciding whether A and B are connected, whether B and C are also connected or not. So those are primarily physically inspired models. And physically inspired models, there are two types, or you can say the model based graphs are two types. One is the physically inspired model, like example diffusion network, and other is a probabilistic graphical models. So probabilistic graphical models are those kind of a graphs where I directly encode the I directly encode what? The graph connectivity by looking at the probabilistic expressions of it. And what is the probabilistic expressions of it? So given the data sets of each point, I will try to learn the distribution of it. Okay. And from the distribution, I want to answer some questions like this. If V4 and V5 are not connected, I want to capture that okay, V4 and V5 should not, if they are not connected, then they are not connected means V4 and V5 are independent given the rest. Given the rest means when I am deciding whether V4 and V5 are not connected, I am also aware that what would be the global pattern between V4 and V3, V4 and V2. So this is also known as the Markov property. So this will try to encode कि if I and J are not connected, then they are conditionally independent. Okay, not just independent, they are conditionally independent. So these seem to be a very powerful way to represent the graph. So if you have done some, if you have a background in the probabilistic model, and these come very often in many of wireless communication study, you need to understand wide stationary signals, Gaussian noise, right? If you want to understand the error function. So I assume that you are exposed to these ideas of it, right? So here what it connects, the problem is something like this. I had thought of using a tab, but that would have made me explain better. But anyway, let's try to understand from just the expressions. So what it is trying to say, it is trying to say something like this. Ki each of these point is here. I do not know the connection, and there are features. So x1 is a feature for this node. So x1 is the data point for this. X2 is a data point for this. So we just have data points, and we have some understanding that I need to be talking, I need to give some understanding if x1 and x2 are not connected, then they should be conditionally independent. So this boils down to the idea of learning a distribution function, a probabilistic distribution function, but not any probabilistic distribution function, learning a specific type of distribution function. So graph-based learning technology, or the graph-based graph learning framework, boils down to the learning of a distribution function. Now there is a connection. Connection is what? Ki in probabilistic modeling, there are like there are different types of distribution functions. Some are and one of the very popular type of distribution functions are exponential families of distribution function, and that we all have used, like Gaussian, Poisson, Bernoulli, exponential. These all distribution functions which we have used so far come under the idea of the exponential families of distribution function. So what they say, ki if your data set is coming from a distribution function, which can be expressed like this, on what it is here. So x is the data set features, and theta is the parameter of the distribution. For a Gaussian case, what are the parameter of the distribution? Can someone respond? If your distribution for your data is Gaussian distribution, then in that case, what are the parameters of this distribution? Okay, I think it's fine. We have mean and variance, right? So mean and variance are the parameters of this distribution, right? Okay. So if you have a multivariate Gaussian distribution, then the mean vector and the covariance matrix are the parameters, right? So these thetas are the functions of those parameters. So what it is saying, when you can factor out the distribution, something where the hx function only depends on the data, and exponential have two terms. So one would depends on the parameter, and other would depends on some transformation of the data. And there is some other term, log of a theta. This may look scary if you have not seen before, but this is the Gaussian distribution which you have used very often. And this is exactly following the structure. So what this is saying, ki if under the probabilistic graphical model, learning of graph is nothing but fitting the data to exponential families of distribution. And when you fit the data to exponential families of distribution, fitting the data means learning the parameter theta. And when you learn the parameter theta, then that theta will directly give you the relevant graph which you wanted to capture. And what is the relevant graph that we wanted to capture? Relevant graph is nothing but the graph which encodes conditional independence. Okay, so see the very connection, how it boils down to the very elementary maths of field, and this is quite useful not only in the abstract mathematical field, this all solves the very fundamental basis of many of the existing machine learning models to wireless communication to gossip algorithms, to many of the phenomena, right? Okay. So the connection is what? Given data, if I can learn this graph using this parameter, if I want to learn a graph, then I just need to find the parameter theta is. So for a Gaussian case, which you have known so far, this is nothing but the inverse covariance matrix. So you must have seen, right? Minus half x transpose sigma inverse x, right? Sigma inverse x. So see, this theta is nothing but the sigma inverse. So sigma inverse is what? Gaussian, the parameter of Gaussian distribution, the inverse of the covariance matrix. Okay. So far, so good. Now, if I want to represent as a represent graph, okay, you need to have some mathematical expressions of it, right? I cannot just write directly. So for a any given graph, there are three popular matrices. One thing is the connectivity matrix, another is the weight matrix, and third one is the degree matrix. And here we are assuming for restricting our study mainly for the mm, positively weighted graph. Positively weighted graph means if 1 and 2 are connected, then the weights would be either positive or 0. Okay. So connectivity matrix will just capture whether there exists an edge between two graphs or not. Adjacency matrix will capture both the weights, whether they are connected or not, but also it will capture with what value they are connected. And degree will encode what is the strength of each node and how you calculate the strength of these node. In general, how you compute, how you know the strength of each person, how connected that person is, right? The more number of powerful friends you have, the more powerful you are. So something similar here also, the same phenomena. So the strength of each node is connected by looking at their neighbors and the strength of the connection. So here for each of the node 1, 2, 3, 4, for node 1, this is node 1. What is the strength of the connection? Which is on node 1, 2, 2, 4. For node 2, 3, 2, 1, 6. Node 3, 2, 3, 5. And for node 4, it is just 1. So these are the three of the matrices. So the idea of graph learning is given X, I need to learn any of these, I need to learn this parameter. Okay. So there is a third matrix, which is known as the Laplacian matrix, which is actually represent the same graph, but have a very nice mathematical property. What is the nice mathematical property? That we will see. But the simple computation of the Laplacian of a graph is you subtract the you subtract the adjacency matrix from the degree matrix. So d minus w is nothing but the Laplacian of a graph. Okay, so now let's see one more connection to it. Do you have any questions so far? We can wait for 1 minute to answer any query, and then we can move further. Okay, so fine. Let's move. See, there is now just try to look at this image, right? There I will also expose you to another idea of graph representation. So suppose initially I just have these features, right? These features with each of the node, and I want to learn the graph, right? And graphs should be meaningful. Okay, so this particular function is doing what? Ignore the LF here. This particular value is doing what? It is looking at the pairwise nodes, okay, and computing the values. Fi is what? The value at the node I, and fj is what? The value at node j. So consider now the value with blue color is 1 and the value with orange color is -1. Okay. So what it is trying to capture is that you sum up the difference between the pairwise nodes. I have, I think, better big picture before. You sum up the difference between these two nodes, okay? And you sum it for all pair of nodes. So now see, when you will do this, okay, what kind of graph you would like to have? Whether when you the V7 and V3 should be connected, or V7 V9 should be connected. Well, I could have, ideally, if there is no connection known to me, I could have drawn a connection between V3 and V7 and V8 and V2. What has stopped me and what will stop me, and whether this should stop me or not, to draw a connection between V2 and V8, V3 and V7, given the signals that we have. Okay, so see, the thing is, the connection graph is meaningful, is to we want to have that kind of a connection where I want to have connections between those nodes which are similar, right? I don't want to have connection between the nodes which are not similar. So how we can quantify when I am only having the nodes available to me, the features available to me, okay, and I want to compute the L, the Laplacian is not given to me. I only have features. But what would be the way from which I can evaluate whether the graph I have learned is meaningful or not? So you can clearly see this graph is meaningful while this graph is not meaningful. And how we can check it? We can check it via this formula F transpose LF, and that will become my objective function for learning this graph. One objective function we have seen before, directly given the feature, if you know what are the distributions assumption on your data, you can directly fit that data to learn the parameter of that distribution. I'm giving you another way that is based on the physically inspired model. So clearly from the image, you can see left of the graph is more important and the right of graph is not meaningful, because they are connecting nodes, they are connecting between nodes which are not similar, right? And that is not what we want. So how to evaluate the and this property, that whether if the nodes which are similar are connected, to evaluate this, there is something called Dirichlet energy as a quantity. So Dirichlet energy of graphs are the representative of whether the graph is meaningful or not. So what you do, you use this as an objective function to formulate your optimization problem. If we will get time, I will go back and will show you also how you can solve the optimization problem and learn the meaningful graph out of it. Let me skip these details, not required much. No, these are, I think these things also will not be able to convince without having pen and paper. Okay, just wait a second. Let me now expose you to some of the popular use cases, right? I think this will be more interesting. I will make it more big picture, not get into the core details of it. Okay, so I will try to connect the whole idea with some of the research problems that I am doing. Okay, that will give you some more context than explaining you the overall details of the algorithmic framework. So I primarily work on the area of graph-based ML, and my research focuses on, first, the theoretical aspect of graph machine learning, and second, the applied aspect of it. So for applied aspect, I collaborate with different folks. So when we look at the graph-based data and general data, there are three core issues that we face very frequently. Firstly, the massive size of the data. One. The data set that whatever we have, whether any domain you pick up, they are primarily biased. So any algorithm and model that we are building, right, they are naturally biased. So how to deal with the biasness and robustness, right? And there is something called distributed. Now, when we are entered into a space where everyone is connected, right? Everyone is connected. And there is a, you can say, hyperconnectivity regime, and there is also called data set is being produced at much massive rate, but at the same time there are domains where we do not have much data. Okay, so I will give you just some context key in terms of building any algorithm. Somehow we have reached to a very good understanding of it, but the main challenge now is not of building a new algorithm for a particular domain. The main challenging is to use whatever available data set that you have. Just to give you some context, suppose there are different telecom aggregators, right? Airtel is there. There are also other companies. They all have massive amount of their data set. Okay, and there are other policies also. But the thing is, now if you want to build a model or build a mini framework, which should be well informative enough of all the aggregators, right? In that case, what we need to see, Airtel will not be willing to share their data sets with the competitor, but they also know that in order to improve their performance, the information or help from the competitor would be also be helpful. So there's something called distributed and federated learning framework. So in federated learning framework also graph based idea comes to the picture. So overall these are some of the challenges, like massive size, distributed nature of the data. Distributed nature for two reasons, because in your case, in many of the cases, there are IoTs and all, they are naturally distributed, right? And there needs to be some aggregation. Another set is because by the rule, some data sets cannot leave that space, right? So thereby cannot participate in the joint learning framework. So thereby there is a distributed network data. I was like, there was one discussion with one of the guy who works for the maintenance of the IoTs for the gas pipelines. Okay, and that gas pipelines, the owner is the one guy. Gas pipeline is cross country, so it runs from Europe to Asia. What issue that he was solving, even if the entire network was deployed by them, but they are not allowed to collect the meter and all the IoT data sets at one place, because there are certain government rules of each of the country. So the same company will not have access to all the data sets in one place. So for those scenarios, you need to have a framework which allows you to not share the data, but still encourage you or facilitate you for a collaborative learning. So those study come under the idea of federated learning. Okay, so now the first mm, area that we touch upon is to have the graph dimensionality reduction technique, and this would be very helpful for you also. So graph dimensionality reduction technique is what? Suppose I have a graph, okay, massive graph. Okay, suppose I want to study the entire network connectivity of pan India. Okay, so that may go maybe 1 million node or maybe 10 million node. That will be a very massive graph. Okay, connectivity pattern, quality of service pattern, customer satisfaction pattern, pan India in one go. So that may have many, many thousands of nodes, but studying those nodes, the whole graph in one go is not possible. So there are two different ways to deal with it. What are those two different ways? One is that you sparsify the graph. What is the sparsification of the graph? Sparsification means the number of nodes remain the same. You reduce the number of edges, the connections. Okay, so that will reduce the number of edges. Another is the coarsening. Coarsening means if I can, some of the nodes which are very much similar, okay, can I compact those nodes into one node, one super node, and can convert 10,000 nodes graph to 200 node graph. The idea is whatever inference wanted to build on the original graph, same inference can you build, or same information can be distilled or can be extracted from the coarsen graph. So this will be a massive boost, right? So this you can see earlier the company, bigger company only can participate in these kind of a learning. Now smaller enterprises also can participate. Next, some kind of analytics can be done, right? Just directly on the edge devices. So this is one of the core framework that we are focusing on. So graph coarsening. So let me tell you the idea of graph coarsening. I will quickly sum up now in next 10-15 minutes. Graph coarsening is the where what we want, given this graph, this is just a toy example. This is a graph, And given this graph, I want to reduce the 5 number of nodes graph into 3 number of nodes graph. A very simple example. This is not only restricting from 5 to 3. You can actually go to 10,000 to 200 nodes also, right? So if the Laplacian of this graph is theta, and the Laplacian matrix, so now just think of the graph matrix. So graph matrix for this graph is theta, then the graph matrix for this graph would be nothing but C transpose theta C. What is C? C is something like this. C says what? At the end, when we are doing coarsening, what we are doing? We are collapsing a set of nodes from the original graph to one super node in this. Okay. So for in this example, you can see what has been done here. It's a toy example. Node 1, node 2 and node 3 have been compressed as one node. That is a node 1 here. So this will indicate what? So the rows are the number of nodes in the original graph and columns are the number of nodes in the quotient graph. So this simply says that the 1, 2, 3 of the original node have been compressed to node 1 in the quotient graph. Node 2 from node in this node 2, the fourth node, this is the fourth node, have been mapped to the second node of the quotient graph, and node 5 is mapped to the node 3 of the quotient graph. Okay. So what is the goal here? Given this graph, I need to learn this graph, but this is not an easy problem. Why this is not an easy problem? Can someone write it quickly? This is not an easy problem because it requires learning C. And C is what? C is a C consists of the binary values. So this is an NP hard problem. Okay, there are NP non-polynomial number of possibilities of combinations, which and then you need to evaluate what is the best one. So overall, graph coarsening framework requires what? Given this graph, learn this C matrix. So once you learn this C, you can use this formula to learn the quotient graph. Your story is done. Now on top of it, what kind of studies we have performed? We will show also what we have done. So now there are many studies. Firstly, how to ensure that you are learning a good quality C. And there are many ways to do it. And some of the ways are very recent and that we have published like in 2024 also, 2025 also. Next, if you have learned C, how you can quantify whether the quotient graph is as meaningful as the original graph. So in this case also we have established there's something called Dirichlet smoothness and epsilon similarity, which says that okay, whatever property this graph we are having, similar property is being distilled into the smaller graph. So fast forward, what we propose to solve the following optimization problem. Following optimization problem says what? I have been given with graph theta, okay, and I want to learn C, x tilde and theta C. And this is the problem that we want to solve. And when we solve this problem, I will get C. Let's not get into the detail of how to solve it. It's an optimization problem and there is a quite an elegant solution that we have provided with certain guarantees. Let's see the connections to it. Okay, let's see more connections that how we can utilize it. So what we have done, so suppose we have solved this and then what we have done further, this appeared in Journal of Machine Learning Research or also in ICML and NeurIPS last year. What we have done here, how we have used it further. So what we did further was we applied into a few applications. Some of the sample applications are here. Firstly, to check whether the deep learning that we will build, the models for deep learning that we will build will be meaningful or not. So in a sense, original graph is there. So instead of training our model on the original graph, which will be very time consuming and very not cost inefficient, and it will not be possible for maybe the persons who are in academia or may not have that heavy level of compute facilities, they may not be able to do it right on the whole graph. So with our method, you somehow compress this graph, okay? And while compressing this graph, okay, you come to a very reduced framework. And while reducing framework, you train the model on the quotient graph. So once you train the model on the quotient graph, you test it on the original graph. So in that also it performed pretty well. Next, what we did, we wanted to study the epidemiological parameter estimation. So when there is any epidemic like COVID and other thing, we need to quickly estimate the parameter of the epidemiological model, like the model. So then generally the contact network of the epidemiological study is quite huge. Just look at the population, right? Indian population. Suppose if you wanted to model the COVID propagation in the study, the contact network may consist of 10,000, maybe 1 million, maybe 2 million in one city or one maybe in one state. Just directly building on that would be very tricky, and the contact network is also expanding, so you cannot, it's not just one time you need to do be doing very quickly. So there we applied this. So compress the contact network. Okay. On compressed contact network, we build this model of the parameter estimation and then tested it. So it worked quite well. Okay. So then we further extended the whole idea of the graph coarsening to many domains, and many results are there. Let's move it. Then we also extended the whole idea of graph coarsening to make it faster. So far, it was an optimization based technique. It was faster. Why I'm stressing on the graph coarsening part, not because I work in this area, but now in terms of there is a big debate, not debate, there is a kind of earlier what was the case, it was the case that academia it was leading research and industry was following us. Okay, but we did. Now somehow the things have started changing. In a sense, the top researchers are coming from the industry, and somehow from academia we are not lagging, but there is some issue, and the issue is not because of the focus. The primarily issue is that the availability of the resources, the compute resources, and many times the data. So availability of the compute resources is not a very straightforward issue. It will be a long fetched. It's a long problem, and it will take certain time to stabilize that everyone has an access to quality GPUs and quality compute infrastructure. But till then, one of the very strongest research frontier would be somehow to scale your model, or somehow to have the same thing being done with smaller model or with a very compressed data size. So what would be the outcome? Suppose if you are a government or you are an agency, and for a massive data sets which were requiring massive amount of compute, if you somehow can compress it, and here I am talking about compression, but there are many different techniques, right? Somehow you can do meaningful compression and then lease out those data sets for academic usage, then suddenly you can see we will be able to do very quality based research, right? Good science with those scenarios. So doing a good compression either at the data set or at the model level is a very important direction for sustaining and accelerating the scientific discovery, because currently everything, there is a connection to AIML model, everyone is talking about it, and the hype is not you can say untrue. It is a reality that AI ML based integration. So it is not just AI that will lead the race, it is AI plus X will lead the race. So a domain expertise will always be required, but not in isolation, because AI is nothing but a smart way of computing it, right? If there is something a smarter way to do the stuff, you should not be just hand waving it. No, no, I don't require it. You have to utilize it, but utilize it by understanding your domain, not ignoring your domain. So in that case, you need to utilize the power of AI/ML. You need to build your own model. You need to build models which are specific to your domain. But the challenge is that the compute is a limitation. How we can deal with that challenge? Integrate somehow the compression techniques. Okay, so I have 2 more minutes there, and I will just quickly tell you one or two more studies. Another line of study is that we have a the thing is, many times when you want to build a model or an algorithm, you want it to be robust. What do you mean by meaning of robust? Robust means if I have learned something or if I have designed something on dataset X, okay, And now instead of that data set X, there is some noisy version of the data that I have received. It is quite true, right? It is true. It is always true. You must be knowing about noise, right? You send a signal X, and when you receive it, it is ideally added by white Gaussian noise or being scaled by some multiplicative noise. So noise is already known. So not always not anytime you receive the perfect data. Okay. So the study of the stability-based analysis is that what if whatever way my model have been trained on some data set X, on some feature X, if there is a distortion in that data with margin delta, then it should not change its output, right? So that is the idea of the robust based study. So there we mapped it to the idea of, and we focused on the graph neural network only. Graph neural network, we mapped it the idea of the Lipschitz stability. So in functions, we know about a Lipschitz function. Lipschitz function is that if your feature inside input to the function is bounded, then output of the function should also be bounded. Okay. So we designed those techniques. So yeah, and then we extended this idea of to the hyperbolic and hierarchical network. In hierarchical network like airport network, disease network, these all are hierarchical network and require different types of maths. So there we extended. What I'm just trying to expose you is that graph-based study is quite important, whether you directly want to use it or not. But you will find it very interesting to interpolate your method with the graph-based method. So very interesting framework which we will show you, which is completely off the shelf, is use of graph ML for geoscience. Two more methods I will show you, and with that I will close. Okay. The idea, the problem here is it's a problem. It's a project that we are doing here at IIT Delhi, and it's a multi department project. The idea here is we are building a gravimeter. And what is gravimeter? Gravimeter is that if I am at a particular area surface, right? If there is a change in subsurface value, then the gravity value will change. So that we also know gravity depends on what? Mass, mass of two objects and the distance between them. So if there is a change in any mass, for example, if I'm measuring of gravity here, the value is Vn, and if there is a cavity, then the gravity value will change. So this is a very sophisticated equipment that one of our team member is building, right? Now our goal is to build a data pipeline for this method, for this system. So the goal here is very simple, but it is also inverse and very hard problem. Goal is you have the gravity value at these measurements, and from here to here there is a change in gravity value. So that is anomaly. So anomaly in the gravity value is given to you. Now you need to tell us whether there is inside there is a cavity or cavity of what shape. Okay, so we'll not get into the details of how to solve it, but we solve it using a graph-based ML pipeline. You will find the paper available on my website. It's a very interesting way how we have it presented by you, and this was only possible because we mapped the problem with the graph domain. Another part where we are using is using the rainfall prediction of Brahmaputra basin. So rainfall prediction means you have the values of the rainfall that happened at one particular you can say weather station. You want to predict for the other weather station, or you want to predict for the next, you want to predict for tomorrow. Another very interesting area, and with this I will close. Okay, the goal here is that in analog circuit design, what happens, you need to do a lot of simulations before it goes to the final layout design, right? You need to perform a lot of simulations using spice simulator and other. This spice simulations many takes a lot of time. Okay, and sometimes it is very also expensive. It is very proprietary oriented, so not every institute have it without without paying for it. So the goal was to, can we build a surrogate of those simulator based on deep learning network. So the challenge was that it required lots of samples, and it was not able to do well. So what we did, we represented each circuit as a node and learned the graph of it. So there the graph learning comes to the picture, and then we applied GNN and run the whole model. Okay, so with this, I think I will close. Just the takeaway point is that the idea of a graph-based representation of the data is quite interesting. It is very flexible, and my whole focus was to expose you to the possibility of it. May not be you may not I may not be able to explain you the complete context of it. But if you are interested in whatever way you want to explore over it, please explore, and you can reach out to me over email if you need more pointers or more references for any of the discussions. Okay, so with this, I will close and I will thank the organizer for this. So, Mr. Ravi and anyone from MNIT, can you please respond?
Yeah, Sandeep ji, I am
Okay,
online.
thank you, thank you. So I have concluded my session and thank you for organizing it.
Yeah, there was. Yeah, participants, if you have any queries, you can post it on the chat. Well, there are. I don't see any questions as
Yeah,
of now, but
yeah, no
the
problem.
participants are thanking you for the session, sir.
Thank you, thank you, thank you.
So,
Okay,
once
so
again,
then great interacting with you, all of you. So I can take it,
yeah, if the
take leave,
participants,
right? Okay,
if the
okay.
participants will have any further
Yeah,
queries later
they
on,
can
they
write to
can
me.
get to you through email.
Perfect.
Yeah. Thank you, sir.